Okay, so today we're going to talk about Ernst Rutherford, who's a scientist that came up with a new, building on previous work of J.J. Thomson, is building up a new model of the atom. And now, along these lines, you are going to need to do some homework. So you need to read section 3.3, questions 1 through 6, page 67. They're due Monday. Do a little warm up objective, and then we'll talk a little bit more about atomic scientists. We won't talk about isotopes today. Okay, so discuss the experiments of Thomson and Rutherford. That's our objective. So, what are the parts of the atom? You guys all know this, so we can just go through it quickly. Electrons, protons, and neutrons. Um, Ernest Rutherford's theory of the atom comes from a key experiment called the gold foil experiment. I'm going to show you a video in just a second. Um, Basically, what he did is he arranged it so that subatomic particles called alpha particles, which have a 2 plus positive charge, are aimed at a thin sheet of gold foil. And Thomson's model is what he was trying to test. Under Thomson's model, the positive charge is diffuse. And so you kind of think as the alpha particles heading towards the gold foil as being like bullets. And if you had just a thin layer of, I don't know, gooey pudding, they should go flying right through the pudding and not be deflected. So he was basically trying to prove J.J. Thomson's theory. He's actually a student of J.J. Thomson's or trained in his lab. What he actually found is that 100% of them didn't go straight through. One in about 8,000 was deflected, and it was deflected at an angle that made no sense if you believed J.J. Thomson's plum pudding model. So let's take a quick look at a little bit of information. So there is a link there, but I'm just going to already have it fired up so I can play it for you.
Hi, it's Mr. Doolin. In this screencast, I'm going to be talking about the gold foil experiment, which was a huge turning point in the development of atomic theory. Before we get started, I just want to give us a little bit of context about where we are right now. We think that the atom looks like this. This is J.J. Thomson's plum pudding model. I tell my students to kind of think of this like a chocolate chip cookie because a lot of American students don't really know what plum pudding is. But this we know to be a negatively charged electron. So we do know what electrons are. That has been proposed. The rest of this kind of area here is positive. So this whole blue space is positive, but we don't know anything about protons or neutrons yet. So that's where we are at this point in time. And Ernest Rutherford actually worked underneath J.J. Thomson, and his team conducted the gold foil experiment, which looks like this. We've got a fluorescent screen, which is important for figuring out what's going to happen. I'll get to that in just a second. But in the middle of this fluorescent screen, which is kind of wrapped around the experiment, is a very thin sheet of gold foil. This is similar to aluminum foil if you think of it that way, except instead of aluminum, it's made of gold. And these are very, very, very thin sheets of gold. A radiation source is introduced. In this case, it's alpha particles. It's important that you know that alpha particles are positively charged. That's very important that you know that. They actually have a +2 charge. And for those playing at home, an alpha particle is a helium nucleus. But the most important thing you have to know in order to understand what's happening in the gold foil experiment is that alpha particles are positively charged. The alpha particles are directed at this thin sheet of gold foil just to see what happens. What's going to happen to a positively charged particle as it encounters an atom? And here's what happened in a nutshell. Most of the alpha particles went straight through the gold foil unaffected. The reason why, or how do we know this, is that fluorescent screen I talked about just a second ago. That fluorescent screen is coated with zinc sulfide. And so when alpha particles come into contact with that fluorescent screen, it'll show you that alpha particle has bombarded the screen at that point. So you almost see little burn marks or hash marks on that screen, and that'll let you know where they went. Like I said, a vast majority of these particles went straight through the gold foil without being directed in any odd way, but some of them started to go off in angles that were not quite expected. In fact, some of the alpha particles shot back almost in the same direction from which they came. And that was a little disconcerting because keep in mind we're understanding the atom through the lens of J.J. Thomson. We think the atom looks like the plum pudding model. So there's nothing that's telling us why would a positively charged particle be repelled or directed away from electrons. So this next view is going to be a top-down view. So this is the view I'm going with. I'm going to show you the gold foil as a bird's eye view with the fluorescent screen in this next slide. Again, we think atoms look like the plum pudding model that J.J. Thomson proposed. So I'm just going to fill in all these red electrons, which are just scattered about, and these are gold atoms, which is why they're a goldish color. The alpha particles, which again are positively charged, should or were expected to just shoot right through these atoms. And like I said, most of them did. But for the times where the alpha particles were deflected, that created a phenomenon that Rutherford's team was not expecting. It was this area right here. And so what he proposed was, let's say that's positive. Let's say instead of having all this positive pudding or the cookie of your chocolate chip cookie, let's say it's all centrally located in a very tiny, dense mass called the nucleus, because that would explain an alpha particle heading that way, hitting it, and being deflected because like charges repel. And so that's where the idea of the nucleus is born. So here are the five major accomplishments of the gold foil experiment. Number one, the discovery of the nucleus. That's very important. Number two, that the nucleus is positively charged. This explains why positively charged alpha particles were being interfered or encountered interference when they hit part or directly head on the nucleus. Number three, that most of the mass is concentrated in the nucleus, and the nucleus is tiny compared to the atom as a whole. Keep in mind, the alpha particles, for the most part, were heading straight through, so they weren't encountering the nucleus at all. For the times where it was deflected, it was encountering that positively charged nucleus, so the nucleus can't be a huge part of the atom. It's got to be very, very tiny compared to the atom as a whole. And then lastly, the atom is mostly empty space. This is kind of weird to think about, but between the positive nucleus and the negative electrons, there is no matter. There's nothing. And for an atom that's incredibly small, that's kind of hard to wrap your brain around. The gold foil experiment was very important in terms of understanding how we think about the atom.
Okay, sorry about that video. The commercials in the middle of the video. They sneak them in now, and I didn't realize that we're going to do that. So anyway, that gives you a video description of it. There's also a picture on the next slide. So you can see this is actually a lead cup. I mean, it's a solid lead box, well, hollow lead box, but it's got a lead lid that you could lift off. They put something called polonium in there. It's one of the elements. Find it on the periodic table. It's down by bismuth, down by Bi. There's a hole in the lead box. That allows the radioactivity, which is emanating from the polonium, which is going in all directions. Well, the rest of it is absorbed by the lead, but the stuff that comes this way goes shooting out. The alpha particles have a 2+ charge. The zinc sulfide screen, wherever a helium nucleus hits, will actually make a mark on the screen. So that way they're able to figure out exactly where they are. And the ones that go off at the crazy angles is why we came up with this idea, or Rutherford came up with this idea, that the positive charge must be in the nucleus. So you wouldn't get things like that if the nucleus wasn't positively charged, wasn't small. Because remember, only 1 in 8,000 is bouncing, so it's got to be very small. And also the mass has got to be there in order to deflect it. So this is another way of looking at Rutherford's model. Basically, nucleus in the middle, very small, surrounded by a cloud of electrons. The atom itself is about 1 × 10 to the -10 meters across. That is really small. To give you an idea, again, we talked about, I think, this before. If you have a pencil and you look at the pencil eraser, the pencil eraser is about 7 million atoms across, to give you an idea. So you can tell they got to be really small. The nucleus inside the atom is 10 to the -15 meters across. Another way of thinking about this, if the nucleus was a dime and you placed it at the 50-yard line of a football stadium, the outermost top row of seats in the upper deck would be about the extent of the electron cloud that surrounds that dime. So they occupy a really, really large amount of space. Because of that, we also realize that an atom must be mostly empty space. Electrons are not big, they're tiny. They're so small we can't even measure their size, actually. So the cloud space is mostly empty space. So who discovered what particle? Dalton didn't discover any. Thomson discovered the electron. And then, of course, Rutherford discovered protons on the nucleus. So those are the three scientists that you really need to know, and you also need to know what they did. You should know Thomson's experiment, you should know Rutherford's experiment, and you should know at least a little bit about the types of experiments Dalton did. You should know their models as well. Finally, I just wanted to show you a little bit of information about protons, neutrons, and electrons. So first of all, look at what I call relative mass. So a proton is about the same mass as a neutron. Now you don't need to memorize these actual mass numbers, but I do want you to look. The heaviest particle isn't the proton by a tiny bit. A neutron is slightly heavier. However, these two are both found in the nucleus, all right? Protons and neutrons. So the nucleus is where almost all the mass is. Electrons are in that cloud buzzing around the nucleus. One electron compared to, let's say, a unit of one mass for protons and neutrons has a mass of 0.0005 units. Really, really tiny. Now, relative charge, neutrons do not have a charge. Electrons have a -1 charge. Protons have a +1 charge. So the question is, how can the nucleus of an atom stick together when you've got all these positively charged protons close to each other in a tiny space? Well, let's see. We know positives repel, right? So they should just fly apart. Well, neutrons actually exert something that scientists call this strong nuclear force. You can kind of think of neutrons as glue that sort of holds the nucleus together. And the majority of the atom's mass is due to that number of protons and neutrons, which are found in the center of the atom.